Next, we're going to be talking about the chain rule in section 3.6. Now, the chain rule is used when we are faced with taking the derivative of more complex functions, such as composite functions, which are functions that are essentially made up of two smaller functions. Here's three examples of some composite functions. Here are three examples of composite functions. We have this one at the top here. We have sine to the -5, it looks like, minus cosine to the 3 of x. And basically, these are just functions that are more complicated, that could be separated into two separate functions. If you look at this little graphic here on top, we have our function g and our function f, and a composite function f or f of g. So let's say if we have the derivative of g of x right here, and we have the derivative of f of x right here, then we can use this equation right here to find the derivative of both of them if they are part of a composite function, if they look anything like the three we see on the bottom here. And this deriving of one function that is inside of another, aka a composite function, is called the chain rule. And as we do some example problems, and as you move on in your calculus learning, you will see that this is actually one of the most common rules that we use. Because most functions aren't just y equals x, or y equals x squared, or y equals sine of x. A lot of functions are going to be quite a bit more complicated and require the chain rule. Another name for the chain rule is the outside-in rule. Because when we have a composite function, the way we're going to go about deriving it is that first we're going to take the derivative of the outside of the function, and then we're going to take the derivative of the inside of the function and multiply those two together. Let's take a simple example. Let's say we have f of x is equal to x minus 1 squared. Well, it kind of looks like this could be two individual functions, and that is the case. We have the function x minus 1 and also the function x squared combined into one single function. So how would we go about deriving this one? First, we have to take the derivative of the outside function, and then we take the derivative of the inside function. Now, a very common notation that you'll see is to have d du. Now, u represents the interior function, which is right here. In our case, u is going to be equal to whatever is inside of the parentheses, and that's usually the case. So, in this case, it's going to be u equals x minus 1. And as we can see here on the bottom, we're taking the derivative of the outside function, which is u squared, and we're multiplying it by the derivative of the inside function, which is just x minus 1. So what do we get as an answer? Well, it's quite simple. We use our power rule for the u portion of this function, which will just give us 2u. And then we use our difference rule for the second portion. So, what is the derivative of x minus 1? It's simply 1, right? Because the -1 goes away, it's a constant, and if we use the power rule on x, it just becomes 1. So, we multiply 2u times 1. And once we're done doing that, we can substitute whatever we had as our u value back in for u, because we're done with all of our derivations. And so what do? We go 2 times x minus 1, and then this whole thing times 1, which just leaves it unchanged. And if we simplify it down further, we get 2x minus 2 as our answer. So f prime, the derivative of the function f of x, is going to simply be equal to 2x minus 2. And this is our entire process here. And that's a very simple example of the chain rule being used. More complicated problems will obviously require many more steps, and in some cases the problem might be so complicated that you will need to use this chain rule multiple times. In fact, that is actually fairly frequent. And we can see it in a more complicated example like this one, where we have to find the derivative of g of t is equal to wow, tangent of 5 minus sine of 2t. As we can see, we initially use the chain rule for whatever's inside the tangent function right here. So this portion right here becomes one of our u's. But we have to use it a second time because within our tangent function we have sine of 2t. So this 2t, we have to substitute a u in there once more, which gets a little bit complicated. But I didn't really want to demonstrate this problem. I just wanted to show that in some cases where a problem's more complicated, the chain rule will have to be used more than once. There's another variation of the chain rule called the power chain rule, which we actually just used in our previous example where we had f of x is equal to x minus 1 squared. These two things are saying the exact same thing. It's just that the top one deals with when your outside function has an exponent, like in our practice problem, and the bottom one is just a more generic version of the chain rule, where you may not have an exponent, for example, with the previous problem here. It is very important to get familiarized with the chain rule because, once again, it's one of the most common rules that we see applied in calculus. And that wraps up section 3.6 dealing with the chain rule. In future chapters, we will do a few more practice problems so we can see how this is applied.